All right, so we're going to take a closer look today at exponential decay, specifically in the forms of tables and graphs. We've spent some time practicing equations and setting up functions that represent decay, but we haven't really looked at them in these other forms. So for our first example, we're going to focus on a pretty typical scenario, which is the value of a car over time. And it says most cars lose value each year by a process known as depreciation. And it's similar to decay, and it means that it's decreasing in value over time. You may have heard that a new car loses a large part of its value in the first 2 to 3 years and continues to lose its value, but more gradually over time. That is because the car does not lose the same amount of value each year, but it does basically lose the same percentage of its value each year. What kind of model would be useful for calculating the value of a car over time? So that's kind of our goal here, is we're trying to create a model given different information in different forms. So let's take a look at our first example here. It says, suppose the value of the car when it's new is $20,000 and it depreciates at a rate of 20% each year. So whenever I'm reading problems like this, I know 20,000 is important, so I like to circle that. And it depreciates, which is a fancy way of saying it's going down in value, at a rate of 20%. Okay, so when you're reading these word problems, make sure to notate the sentences as you go. The car is depreciating at a rate of 20%, and we've practiced this for a while, but just to review, we always start with 100% of what we have, and then we either add or subtract the percent change. So in this case, since it's depreciating, we would subtract 20%, and that would leave us with 80% of its original value each year. And that's basically what I have written right below here. I just wrote it out for you. So that's how we find what we call the common ratio, which is what we'll multiply by in the problem when we convert this percent to a decimal. So we need two things. We need the initial value, which is also called the y-intercept sometimes, and it's its value at 0. And that's what they gave us right here. Its initial value before any time has passed is $20,000. Okay, and then since it's losing 20% a year, we keep 80% of its value each year. And then we make it a decimal, right? So this is the percent. We don't write the percent though. We write it as a decimal, which moves it 2 places to the left. So 0.80 is going to be what we actually multiply by. So let's take a look at the depreciation data over a 5-year period of time. Complete the table, round to the nearest cent. So we're going to fill in these missing values here. I've already started you off here with the easy one. So at 0, it's 20,000. And then you can take your calculator and do the trick we've been doing in class with this, which is to type in 20,000, hit enter, and then put times, that's a times, and then we're putting the decimal 0.80. Remember, we're not multiplying by 80% because that would actually make it get really big really fast. And as nice as it would be for my car to gain value that quickly, that's not how it works. It actually loses value because we're multiplying by something less than 1, 0.80. All right, so if you have your calculator in front of you, this is what you would want your screen to kind of look like if you were doing what we've practiced in previous units. So you're just going to record. Again, I had the first two for you in the table, so this would be for 2 years, 3 years, 4 years, and 5 years. And you can leave up to 2 decimals with money, but we're about to graph these, so if you want to round to the nearest dollar, that's also fine. Okay, so getting the numbers from our calculator, we should get $12,800 for 2 years, $10,240 for 3 years, $8,192 for 4, and then $6,553.60. I like to put it like dollars and cents there. So that was one way you could generate this. You could also kind of skip ahead here to part C and write an equation for it and then go type that in Y1 and look in your table, which is another thing we've been practicing. So let's go ahead and figure out what that equation would look like. Right? An explicit equation. Oh, whoops, that's part C. Let's do part B. Let's go ahead and graph it. This is kind of the less fun part, but it's something we have to be able to practice. So I'm just going to label my vertical axis over here, the y-axis, as value of car over time. Okay. Which is our money. And as you can see, our money does not go up as we go from year to year. It actually gets smaller, which means that our initial value, our y-intercept at 0, is actually the largest number we need to reach. And I'm going to put this in thousands because I don't want to write a bunch of little zeros. So like when I put a 2 right here, that stands for 2,000, 4,000, 6,000, and so on, just for the sake of space. Okay. So that's at 0, and then going along the bottom, this is our independent variable, which is number of years. And these are just going to be pretty normal. So we've got 1 year, 2 years, 3 years, 4, 5. We don't go past that. You can keep labeling if you want, if you're like me, but you don't really need to. All right, so this is our special value. This is our initial amount at 0, which is also called the y-intercept because it's where it touches our graph over here on the y-axis. So linear functions have y-intercepts, quadratics, which we'll get to soon. All the functions we work with have this special point on the y-axis, and it tells us what we start with before anything else happens. Then at 1, we're at 16,000. And we drop to something right below 13,000, so just a little bit. Oh, and 13 we don't see. So 13 would be directly between here, and then I would just drop a little bit lower than that. So you can kind of eyeball it, but I just cheat and draw really big dots. So you can't tell as well. All right, and then 10,240, again, is going to be right above 10,000, but not much. And then 8,192, again, right above 8,000 by a little bit. And then 6,500 something, so halfway between 6 and 7. And 7's halfway here, so kind of like a fourth of the way up on this last one. In that general vicinity. So it's not the easiest to see, but knowing that it's not linear, we know this isn't technically graphing a straight line. It's just a very gradual curve. So you're going to take your pencil and you're going to try your best to make a nice gradual curve out of these points. And then we're going to put an arrow at the end. All right. Any exponential function should be curved even if it's not super drastic. It will not be a straight line because we're clearly not changing the same amount each time. It's different. It's by a percent. So now let's write our function. So we're going to say y equals the initial amount at time 0 right here, which is our y-intercept, times our common ratio, or the thing that we multiply, so how you start and how you change. So times 0.80, which you can just write as 0.8 to the x. Use this equation to find the depreciated value of the car for year 8. So year 8 is when we go to our table and we look at x equals 8 and figure out what the output is. So let's go back to our calculators. Okay, so if you remember to type your equation in, you're going to hit y equals at the top, and you're going to type in and make sure you put the right number of zeros, 20,000, parentheses 0.8, and then to the power is the caret button under clear, and then x is the symbol button. So go ahead and do that. Get that in y1. And then to get to our table over here, you're going to hit second graph, which is the blue word above table. And we're going to use this table to answer the next couple questions. So the first question said, for part D, it says, use this equation to find the value of the car for year 8. So you're going to come down to year 8 and you're going to look in your table, and you can round to the nearest dollar if you would like, or keep 2 decimal places because technically that's what money has. So in this case, that looks like 3,355.44. We'll go with that for year 8. Let's go write that down. All right, so that's going to be, put a dollar sign, and we're going to say $3,355.44. And now we'll answer the next question, which is, between what 2 years will the car be worth $5,000? Okay, so just make sure you pick, it's easy to pick one number right and then go the wrong way, so to speak. So especially when it's going down. So 5,000, I see 5,000 something right here. So the real question is it 5 and 6 or is it 6 and 7? And it's easy when it's going down to get a little turned around here. So if you look here, 5,000 down to 4,000 is where it's actually going to cross the $5,000 we're looking for. It has to cross through that to get to the 4,000s. So we're actually going to say between years 6 and 7. So between years 6 and 7. Great. Let's turn the page. So this one's a little bit more compact because I'm not making you graph it or do a table. It's kind of more of what we've already been practicing. So number 2 says Matt bought a new car at a cost of $25,000. The car depreciates approximately 15% of its value each year. So this is the question we have to make sure we practice, because if you get the common ratio wrong, you're going to get everything else wrong. So we always start with 100% of what we have, and it says it's depreciating, which means going down 15%. So we're going to subtract that, and you can use a calculator if you need to, but hopefully one way or another we'll get 85%. And then to actually make that a decimal, we have to move the decimal place over 2 points. So we get a ratio of 0.85. And that's what we want to write right here. Okay. Write an equation to model the decay value of the car, where y is the value and x is number of years. So let me erase this so I have some space here. So I'm going to write y equals the initial amount, the y-intercept at 0. It's worth $25,000 before any time goes by. And then each year after that will multiply by 85% of its original value to the power of x. And then what will the car be worth in 10 years? If you have a question where it's just wanting one thing, you can still use the table option. You could also just plug it into our equation since they just have one question for us. So 25,000 times 0.85 to the 10. And you can just type that in your regular calculator screen. Okay, and I've kind of pulled my calculator up here. Again, I'm still learning how to use this fun little gadget. You're going to type in our equation, plug in a 10, and then this is the number we're about to round. So we'll say that gives us a money value of $4,921.86. And that's all there is to that one. So for our last big problem here, another table and graph. Okay, because these depreciation ones are a little bit harder than the growth ones for us. It says the cost of a new truck is $32,000 and it depreciates at a rate of 12% per year. Okay, so let's go ahead and figure this out for the table. I know 12% is what I'm losing. So if I start with 100% and it's depreciating 12%, that means I'm left with 88% of the original value year after year, which means what I'm going to multiply by is 0.88 for my ratio. Okay, so I've got my initial amount already plugged into the table for you, and then we're going to multiply in our calculators times 0.88. So you can do that either way. You can do the typing in the initial, hit enter, or you can try to come up with equation, but I'm going to stick with the easier one for now. Alright, so I got my calculator pulled up. Hopefully you do as well. So I typed in the first number and hit enter, and then multiplied by my ratio, and I'm just going to round to the nearest dollar because we're going to be graphing it on a really large scale anyway. So let's see. So after 1 year, it's to 28,160, then to 24,780, then 21,807, and then 19,190, and 16,887. All right. So now we're going to get ready to graph this. So I'm going to label again. My dependent on the y-axis is going to be the value of the truck. It's usually whatever we're actually measuring over time. And just like last time, I'm going to put in thousands, so I don't have to worry about writing out a bunch of zeros on my axis. Ooh. Okay. And this time I'm going to go by fours instead of twos, 4,000s, because this one gets a little bit higher than our last one. So 20, 24, 28, 32 is as high as we need to go because really it just goes down from there. I'm going to keep labeling just for the sake of it, but that's really as high as we needed to get. Maybe I'll stop at 40. Save us some time. Okay, yes, so our y-intercept, or starting value for our next graph here, is 32,000. So that lands nicely right on a grid. Then 28,000-ish. So, that's right, forgot to label the bottom. So that's going to be number of years again. And that's going to be 1, 2, 3, 4, 5. Okay, now we're good. So then at 1 year, we're a little bit above 28,000, but basically on it. Then 24,700. So basically kind of close to 20. Ooh, this is harder because it's going by fours. So 24's here, 28's there. Directly in the middle is 26. So if I want 25, it's going to be even below halfway. A little bit below halfway. Then 21,000 is like a fourth of the way up there between 20 and 24,000. That might be a little too high. I can't tell. And then 19,000 will be right below 20,000. And then 16,000, closer to 17 though. Here in that area. Okay, so again, I know it's not linear just because I didn't add to get our table. We had to multiply by 0.88. But again, it's a very gradual curve. So you're going to connect these as best you can, but the idea is we know it's going to start slowing down here. Alright, so find the initial value. Initial value on a graph is the y-intercept. In a table, it's at 0. In a word problem, it's whatever you start with before any time goes by. So for each of these, we can see it's 32,000. Common ratio is what I multiply by. So 0.88. And then I can write my actual equation. So the y-intercept is always written first, then the growth factor to the x power. And now we're going to use that with our calculator to answer these two questions here. Okay, so again, you're going to go into y1 and type in your equation. Okay, and the first question asks us to look at 4 years old. And so in our table, we can see at 4 years old, actually that one was on our paper. We didn't even need our calculator, we already have found it. So when it's 4 years old, we're going to say it's $19,000 and $19,190. In our table, it does tell us a more accurate amount of 0.25 cents. Then it says, how long does it take to reach half its original value? So this is kind of a two-step question. So if it started with $32,000, half of $32,000, this is really asking us, when is it $16,000? So you could just take $32,000 and divide by 2 if you're not sure. But that's really what it's asking when it says half of its original value. So we're going to look in our table now for this. All right, so now we're looking for $16,000. And it's getting less. Oh, I see a 16. So it probably has something to do with year 5. The question is, does it cross through 16,000 from 4 to 5 or 5 to 6? And as you can see, 19 to 16 something wouldn't cross through 16,000 even. So it must be between 5 and 6. All right, we're almost done. Hang in there. Last one. The cost of a new ATV is $7,200. A formula that represents this, so this time they're giving us a formula, is right here. So by what percent is it depreciating? So that means you need to take a look at this decimal, 0.82. First, ask yourself, what is that as a percent? Which simply means we move that decimal 2 to the right or multiply by 100. And that would give us 82%. So it's keeping 82% of the original 100%. So how much did it have to go down? Right? That's what you're basically asking yourself. So if you can take your calculator and subtract them if you need to. But that means that we lost a total of, 18%? Like if you made an 82% on your quiz, that means you lost 18 points, right? So that's the amount or the percent it's depreciating by each time. All right, and for these last two, we're simply going to type in the equation provided to us by the problem into y1, and we're going to use the table to answer both of these questions. So the first one says find the value at 10 years old. So if we scan down here to 10 years, we're going to see it's worth, $989. And then we just used 2 decimal places. So, I guess technically that would round to a 3. So $989.63. And you could also get that by simply plugging it in on the regular calculator screen if you wanted to. That is what you're technically finding. And we're getting $989. Ooh, that was ugly. And 63 cents. Last but not least, after how many years will the car be worth $5,158? It's nowhere down here. This is 500, so be careful. $5,158? Well, it started at $5,904, and then it dropped immediately to $4,000 something. So that means we're actually looking right at the beginning, so between 1 and 2 years. All right, so this concludes our notes on exponential depreciation problems. I hope it helps clear up some things with that exponential decay stuff. And now you probably have instructions on what to do next.